Hello and welcome to ResearchPod. Thank you for listening and joining us today. In this episode, we look at the work of Professor Joe E Heimlich and colleagues from the Center of Science and Industry, a science museum in Columbus, Ohio, USA, who investigate how we learn when we visit informal learning institutions, such as museums and aquariums. This project involves a series of studies spanning 11 years that focus on visitors' experiences of visualizations together with their learning behavior and data visualization literacy. How do we learn in non-formal, non-school settings? This question is at the root of work being carried out by Professor Joe E Heimlich and his colleagues in the Center for Research and Evaluation, or CRE, based at the Center of Science and Industry, or COSI for short, a science museum in Columbus, Ohio, USA. The CRE team investigates the learning behavior of people visiting informal learning institutions, such as museums, parks, zoos, nature centers, and aquariums. Heimlich remarks that the CRE's laboratory is where people are learning. The team's location within a museum encourages the researchers' creativity, enabling them to pilot test their innovative research tools and instruments using COSI's visitors as subjects. These trials enable the team to collect data that stands up to questions of rigor, meets all ethical standards, affords the correct depth of information, and is underpinned by learning theory. The CRE's creative research builds on previous methods developed by other social science researchers, analyzing museum visitors' behavior. The team insists that their data collection is integrated into the visitor experience and takes an engaging, fun approach that contributes to the visit experience. Games and gaming inspire their data collection instruments. The researchers explore various ways to collect information from visitors while contributing to the visit experience and even visitor learning. An underlying goal for CRE is to give visitors an opportunity to participate in research in ways that make their interactions inherently meaningful and lead to greater respect for participation in the scientific process. This has led to CRE being recognized for its creativity in gathering data that is both rich and rigorous. Heimlich explains how their research methods evolve. Instead of carrying out one main study, the CRE team often engages in long-term collaborations and performs long sequences of individual studies, each providing a better understanding of a particular aspect of learning behavior. These studies can involve extended collaborations with researchers from other institutions. One such extended collaboration has involved investigating the data visualization literacy of visitors to science museums, as visitors can sometimes find data and visual presentations of data daunting to interpret. The widespread use of data visualizations for big data, that is large, diverse data sets that can grow rapidly, assumes that viewers can interpret and understand the visual. But is this assumption regarding viewers' perception true? Collaborating with Dr. Courtney Borner's laboratory at Indiana University, the CRE team have carried out research into big data and data visualization over a period spanning 11 years. This has involved a long series of studies focusing on various aspects of data visualization literacy, together with the visitor's experience of visualizations. The collaboration's first study compared how people interpreted 20 different types of big data visualizations. Data visualization involves the representation of data using graphics, such as charts and infographics. These visuals are intended to communicate complex data relationships in ways that are easy to comprehend. This multi-phased investigation took place within informal learning environments in 3 U.S. science museums and aimed to find out how familiar visitors were with different visualization types. The researchers created a visualization framework made up of 20 charts, graphs, geospatial maps, and network layouts. Participants were each shown 5 of the 20 different visualizations and asked if the type of data presented looked familiar, where they might have seen similar images, and how they would read the data. They were also invited to name the specific type of visualization and specify what types of information should be included in each type of visualization. The results show that while most participants were interested in maths, art and science and often encountered visualizations, many had difficulty interpreting and naming them. Partakers tended to be familiar with basic charts, graphs and maps. Only a few had encountered network layouts, and hardly any could read the network visualizations. These findings support the findings in other studies in formal education and science communication, that members of the public tend to possess rather low levels of data visualization literacy. This study raised more questions, prompting further study to find out if people were able to understand data visualizations better if they constructed or deconstructed them layer by layer. Although people usually deconstruct visualizations, from a literacy perspective, the researchers wanted to explore whether it would be helpful to build the visualizations with the visitor. Museums often use visuals such as diagrams, timelines, and maps to showcase data for their visitors to help them understand social, temporal, and spatial relationships. In this second study, the CRE research team created the Simplicity Familiarity Matrix to support museum professionals designing materials for exhibition spaces to facilitate the creation of visualizations that can be interpreted by visitors of all skill levels. Visitor studies were performed in 4 science museums and an aquarium using booklets containing the layers required to construct the visualizations. Visitors were shown the base layer and asked to interpret it. Then they were asked to describe what the base and first layer were communicating, then the base, first and second layers, and so on until the construction of the visualization was complete. The team found that data visualizations range from simple to complex, while the data they depicted stretched from familiar to unfamiliar. By overlaying these two continua with visualization running horizontally and familiarity running vertically, the researchers created a 4-quadrant graphic, a simplicity familiarity matrix that museum professionals can use to inform their designs for interpretive materials. To enhance visitors' experiences of data visualizations in museums, the CRE team recommended using easy-to-understand, well-designed data visualizations while providing appropriate guidance and support for visitors. They suggest employing a range of sensory modes, such as visual, kinesthetics and auditory, and using a selection of static and dynamic formats. They also advise that data visualizations are made relevant to visitors, for example through personalization. Participants tend not to criticize the finished visuals in an exhibit or a document, so the researchers wanted to investigate what level of finish draws the most honest criticism and critical examination from visitors, so that studies with visitors would provide better data. The findings of the study are still in draft format, but revealed that fewer critical comments were made on a well-designed, print-worthy map, even though it had the same errors as the others, not quite finished versions. When the data collector pointed out the error, some visitors said that they noticed it but didn't want to mention it, while others thought they might be wrong rather than the map being wrong. The Science Museum of Minnesota had developed an interactive run exhibit where a visitor's running time is automatically measured and then displayed. The National Science Foundation funded project team developed a similar walk experience that recorded an individual's walking time, as many museums discourage running. Using X macroscope, visitors could choose to enter non-sensitive personal data into the system, e.g. age and gender. This data appears on-screen as part of a visual, such as a graph or a map, so when someone crossed the finish line, they could see themselves in the data compared to other visitors. Participants could also manipulate the data using the X macroscope technology to create their own data visualizations. To support this work, visitors' social comparisons were investigated on 2 levels: who visitors chose to compare themselves with, and which data they considered most interesting to compare with others. The researchers also explored how X macroscope could be adapted to other physical experiences for data visualization literacy applications in other institutions. Heimlich describes how these grant-funded projects resulted in new technology for creating real-time data visualizations with visitor-generated data. CRE was tasked with finding out what people understand about data visualizations, the types of data they are interested in comparing with others, and who they want to compare themselves with. They also established how people make meaning from data visualizations and how willing they are to offer honest critiques of the visualizations. In addition to informing the project, these findings make a significant contribution to the body of knowledge concerning how people understand data visualizations, in both terms of academic literature and support for museum professionals designing informal learning material for exhibition spaces. That's all for this episode. Thanks for listening. Links to the original research can be found in the show notes for this episode. And, as always, stay subscribed to ResearchPod for more of the latest science. See you again soon.